Thank you very much. Dear my friends from abroad, and dear Christoph, could you let me speak Russian? Because it will be much more comfortable for 95% of the participants. And just because my English is not too, it's too far from perfect.
Sure, speak in Russian, then I can test the English translator and so on.
Yeah. Of course, it's a great honor for me to be invited to so famous conference Samara BCI 2020 and to join so famous speaker company. I already impressed the presentation of Samvan Lee and Janishi Yusheba and also Alex Asachi and Sergei Shishkin and Vadim Nikulin, and a lot of thoughts came to my head and was born in my head, but nobody read that thoughts by BCI technology. Why? What has happened 30 years after the first good system for BCI technology? In Russian. So, действительно главная задача, которая, вообще говоря, стояла перед нейроинтерфейсными
that was faced by all of the BCI technologies was mind reading. I'm not sure how to translate it into Russian correctly. So we started developing BCI interfaces to read the minds or to read the thoughts of different people. Unfortunately, this task still remains unresolved. We have developed many different methods, but I would like to take a bird's eye view of the problem. During this week's conference, we will present several speeches on this issue. We will talk about different applications of BCI technologies, but I would like to take a bird's eye view of the problem, as I had already mentioned. So let's look at the brain computer interface markets by type and application. What is happening when we look at the number of different application cases, or on the when we're looking at the number of different developments in the world. Of course, all of the technologies can be split into two big groups: invasive, non-invasive. There are also semi-invasive technologies. For instance, when the electrodes have passed the cranium but haven't touched the dura matter. So once the dura matter has been penetrated, the technology becomes fully invasive. What Alex Asachi has shown can be attributed to semi-invasive technologies because we do not touch upon the cortex itself. All of the microgrid has been placed on the brain. So what is happening with invasive and non-invasive technologies? As you can see, the year 2019 marked a significant difference between invasive and non-invasive technologies. But if we were to talk about the trends that is developing until the year of 2027, then we will see that the number of non-invasive technologies will multiply, but the invasive technologies will multiply even more by the year 2027. So such a difference between invasive and non-invasive technologies, if you look at these two columns and the height of these two columns, this difference should also be correlated or adjusted, because when we're talking about non-invasive technologies, of course, we are talking about visual games, technologies, entertainment, but invasive technologies are only limited to healthcare and medicine. Let's see what happens with different applications. As you can see here, when it comes to applications, video games and entertainment are leading the way, but closely followed by technologies developed for the healthcare. It might appear a bit strange, but there are also some BCI systems being developed for the smart home applications. Healthcare is the leading application field for BCI. So from this point on, I will only be talking about healthcare applications of BCI. You all know about the BCI Horizon 2020 European program. And under this program, you see a pipeline that's been developed. You see on the y-axis the reliability, speed, and accuracy of BCI systems. And here, well, here we are, somewhere in the middle of this graph. As you can see, invasive technologies gain popularity, are gaining popularity as we speak, which means that by the year 2025 or 2030, they will have acquired full speed. Therefore, both implantable, semi-implantable, and wearable technologies, invasive and non-invasive technologies will coexist together in the future. But why do we need non-invasive technologies? Well, the European program gives us 5 categories to replace a lost function, such as spellery. You know, the way that the spellers are used, well, we do not fully restore the speech function, but we can replace it. The second way is to restore a function. For instance, we can restore motor functions and so on. We can enhance a function or optimize a function. For instance, if we have BCI systems which use neurophysiological data to detect a person's cognitive load at any point in time, and they can optimize information input. The next way to use BCI technologies is to improve an existing input. For instance, in our lab, we developed an approach using transcranial magnetic stimulation to gain an advantage during motor imaging training. And the last area of application of BCI is research. So when it is used for research and the advancement of science. You know, I used to believe that BCI technologies are not just developed to address an existing problem, but it is a really powerful paradigm to understand the human brain.
This was an overall overview and a general overview. We have everything represented now. Some is more or less developed, but everything is there. By 2035, the words will be decoded and the entire speech will be decoded in 2035. When we talk about restoring movement, if we already decode some movement signals in 2035, there will be complicated movements that be decoded. There's intentions for a complicated movement. This progress is quite significant in the next 10 to 15 years. At the same time, it doesn't say that we will be able to fully ensure direct interaction between the brain and the external actuators. But what do we have now? For people who are fully in a coma, or there are technologies to get connected to them, of course, controlling neuroprosthesis, it already exists. And we are all aware of 2012 when a couple of American laboratories showed a patient controlling the manipulator with, of course, invasive technologies, some hybrid technologies. When BCIs are controlled, or rather control the muscles of the body. This FES is used, this intention to move is marked as a movement of a muscle. If something happened not in nerves or muscles, but in the coordination of neurons on the cortex, which cannot issue the command to the muscle. And of course, finally, we have those devices that replace or restore speech. And we have our new chat technology, not just a speller, but a commander that can issue commands to external actuators, and you get emails and go online and so on. That's full replacement of communications that already exist. Finally, another technology that we really need when you stimulate the spinal cord, but instead of using buttons, when the patient himself or herself turns on, the stimulation has to be turned on by the person's intention. It has to be connected to the spinal cord. And some works like that are already there, and this is the technology that we already have. Without BCI, we had deep stimulation technologies for a number of reasons, to work with tremor or epilepsy, and that already exists. But these devices are being developed, and they need feedback. They need to be able to monitor how efficient that stimulation inside the brain is. And then we will have a real BCI system. It already works, and it's already being studied, and there are about 200,000 people in the world living among us, and they don't feel epilepsy or seizure due to the help of these technologies. Finally, bionic prosthesis and bionic hands existed for a long time, and Russia actually is the birthplace of those prostheses. But controlling these prostheses is quite complicated. Some of them are already in the market, but they need to get this controls or feedback from the brain. At least our next task is to make them be able to feel the touch in such a way that we could send this feeling directly to the brain. The brain should feel that the prosthesis touches different objects. That's already well known. It was already presented here in Samara too. What else do we have in the pipeline? We need to somehow help the cognitive abilities of humans. As we use EEG or other neurographic or biographic values for the activity of brain, we need to understand how high the cognitive load is. It's very important during training. If you give too much load, people won't be able to do it. But if you combine it with some additional BCI systems, and the system would know how much the brain can take in, not even consciously, but how much of information the brain can take in, the training systems will be more efficient. This is also in development. I have not found any conclusive data on that. Of course, here we have computer games, and we enhance people's gamer abilities, but in reality, these are cognitive abilities. This is short-term memory, attention, not just time for motor response, but to sense a motor response to what you see in front of you. All these functions can be trained, and there are lots of developments about adding BCI technologies into gaming or gaming control. Also, it's moving BCI technologies to understanding what the brain does. We had a debate already here, started by Sergei Shishkin, about consciousness. This is one of the higher functions of the brain. It has lots of functions, but even if consciousness is out, the brain keeps working. How to get in touch with it? That's the task for the BCI technologies. And you can look at the brain mechanisms at the subconscious or unconscious level, and there are lots of them. That's very important. And finally, neural interfaces in the reverse sense, not the ones that transform brain commands to external devices, but on the contrary, take extra external commands and send them to the brain. We're all aware of cochlear implants and even retinal prosthesis, and this technology already works. There's a broad range of technologies that even now are in operation, but there are also limitations. I show some of them here that exist, and they have been with us for a number of years, and it's really hard to overcome them. What are these limitations? There's a very slow command transfer rate, 20 bits per minute, 5 to 8 letters per minute. If we talk about a speller, that's not enough for a healthy person, while they can type 100 letters a minute from the keyboard. And these limitations are still there. The second limitation is that there's too much resources for memory and attention are taken by these technologies. The subject has to be as attentive as they can when they imagine a motor image for the BCI to work. Will it be useful for a healthy individual? Imagine that you cannot learn the subconscious control of the bicycle. Imagine that you have to control every movement while you are on the bike. But this is what is not happening with BCI, or there's very little progress. Our short-term memory and attention and vigilance are overloaded. You cannot do anything else but work in the BCI contour. Let's get back to decoding the intentions of thoughts. It's really hard. Today, when we talk about motor images, we can decode 4 or 5. Correct me if I'm wrong. We can decode 5 or even maybe even 6, but with 5 you get lots of errors. Why is that? Why cannot we decode using EEG? Why cannot we decode, I don't know, an orange or a steam engine or something else? What prevents us there? All right, EEG is not the brain doesn't use EEG for information exchange, but it's really hard to do even if you use invasive technologies to sort of dig into your specific thoughts invasively. And the main limitation here is that we are using to detect different subjective psychological factors. We use correlates, neurological correlates of those psychological acts, but not the actual codes that the brain actually uses. My next point, I already said, how we cannot detect more than 4 to 6 images. The accuracy is insufficient. There are lots of errors. Even if we make a random selection 1 out of 2, you get 20–30% error rate, even in the best systems. And finally, what I want to mention, any such system, for them to work reliably, they have to be trained for a long time, from 50 to 100 sessions. So in conclusion, are there any prospects for the future? This is a very quick spelling interface, 175 bits per minute, as opposed to 24 bits per minute, working using induced or event-related potentials or evoked potentials. And you can see how the letters are typed really quickly. This technology allows you to type really fast, but the environment is so aggressive, you cannot stand it for too long. We had a system like that in our laboratory that got 149 bits, but it's more milder on the patient. And we also spoke about decoding and detecting speech, but how much of that is decoded really from 42 to maybe 30%, and that's with limited amount of words. So that's a long way from decoding normal speech. And as we decode movements rather precisely, but there are still quite a few errors with only a few commands. And this is my conclusion. The main problem of our reason why we cannot talk to the brain directly is because we don't know the code of the brain. If we knew those information modules that communicate within the brain, we would intercept these signals. That if we knew those codes, it would be easy for us to control. But we don't know it. We use the correlates that sort of look for those signals through trial and error by training the artificial neuron networks. Is there a way out of the situation? Yes, there is. And our latest studies that I have shown indicate that if we combine BCIs with AI, but not to create classifiers of what's already in the brain, but for them to talk to another, the brain is quite flexible. It will find a way to change its electric activity to make the AI understand its activity better. And the AI, on its part, as it trains, will be finding the meaningful facts that will give you results. And in this two-way channel, there will be this real brain-machine language of speech. And this will be a new signature on the new foundation, after which you will get real interactive interfaces where brain interacts with computer or AI directly. Thank you for your attention.